Hello, here we talk about geometric meaning of solutions of linear systems. We will look at examples where we can draw geometric shapes corresponding to solution sets. So if we have two equations on two unknowns, that corresponds to looking at intersection. If we're solving a system, we're solving each equation separately, and each equation gives us a line on a plane with xy coordinates. Well, it is a line if the equation is not totally zero. And in generic position, two lines will just intersect at a given point. That is the case where we have a unique solution, where we have both our unknowns being pivots. But there are degenerate cases where we only have effectively one equation, where the second one is proportional, or at least the left-hand side of it. And in that case, we will have just one line. If both equations are just scalings of each other, if the second equation is really c times the first equation, then it will be c times c. And the first is here. We are solving for the same line twice, and the solution set will be just a line. So that will be the case where we only have one pivot, say x or y. And the last case, when we cannot solve the system, corresponds geometrically to the situation where we have two parallel lines and they don't intersect. And that would correspond to the equations being proportional to each other on the left, but not on the right. So the second equation is proportional to the first in its left terms, but the free coefficient f is not proportional to that free coefficient of the first equation. And that corresponds to still having one pivot, but being inconsistent for the system, no solutions. And that is all what can happen with two equations if we disregard the sort of totally degenerate case where all equations are zeros. The next case we could geometrically draw is the case of three variables, three unknowns. In this case, we will have geometric shapes inside the three space with coordinates x, y, z. And in each equation we're solving, so equation of this shape corresponds, so solution set of this linear equation, if it's not total zero, will give us a plane in the three space. So this is a portion of this plane. And if we are solving two equations, then generic situation is that we will have two planes, and generically they intersect at a line. And that means that if we're solving a system of two equations in three unknowns, we are going to have a one free variable which will be measuring our position along the line. So we're going to have two pivots because only two equations we start with. But that is only a generic situation. We have still have possibility for degenerate cases when these two planes are actually the same. or when these two planes are parallel. And in this case, we will have only one pivot, but depending on if two equations we have are just proportional throughout, or if they're only proportional on the left but not on the right, then we will have either two-parameter solutions or two-parameter solution or no solutions at all. Now, if we have three equations on three unknowns, that would correspond to the case, to the situation where we intersect three planes. And the most generic situation, most generic position they can be in will be this, and then the intersection lines will be like that. And the most generic situation of those intersection lines, there are two lines sitting on each of those planes, and generic two lines intersect at a point. So that will be the case of three unknowns, three equations system, which will have three pivots. No free variables, just unique solution. But these degenerate cases will give degenerate cases of three equations. So two equations are just totally proportional out of three, and the third one is something, and then it would mean that we would have two planes coinciding, and then the third one being just different, and the intersection will be a line. So that will be the case of two pivots, leaving us one variable free, and that variable will be measuring position on this intersection line. And in the second degenerate case, we will still have a third plane somewhere intersecting the two, for example, in these two parallel lines. Still, these two parallel lines will not intersect themselves, so although we'll have two pivots, in this case, we will have no solutions at all. And there could be one more, even more degenerate case when the third line is the same, the third plane is the same as the two coinciding planes. That will correspond to the case when all three equations are just proportional throughout. So that will be giving us the plane, just total the total coincidence of the three equations. All the three equations are proportional, and that will correspond to the just one geometric plane. So we'll have one pivot, and the remaining two free variables will be determining the position on the plane. And of course, we could have, with these two planes being parallel, we could have the third plane being one of the two parallel, so one will be doubled, solved twice for, and the other will be still parallel, so there will be still no solutions. Or we could have three parallel planes. So equations are proportional in their left sides, but right sides are all not aligned, and then we'll have three parallel planes, still no solutions. And if we'll be solving the system, we'll still have one pivot. That is not all. We could have two first equations giving us generic position for the two planes, like the flat one and the one facing us. And the third one, or maybe the flat one and the one which is sort of h-word toward us. But the third plane might still be intersecting the first along the same line as the second. So we'll have the second, say, slightly tilted to create more space for the third, and the third will be like that. And the total intersection is still this line, so we will have two pivot situation and one free variable, giving us this freedom for solutions. And that is almost all, apart from the last case where we have three planes. In each of them intersect along a line, of course, and these lines will be parallel to each other. So the intersection of this plane and this plane will be that line. Flat plane and this tilted plane will intersect along this line, and the remaining two intersect along this line. So we'll have three parallel intersection lines for each of two of our planes, but these intersection lines are parallel and they don't meet. And that means that although we have two pivots, we still have no solutions. So the solvable cases are here, just to recap, and they correspond to either having no free variables, having one free variable, or having two free variables. And that is all we can have for solvable systems. Non-solvable systems could be non-solvable also in many different ways. And the final comment is when we actually solve a system using Gauss elimination, what we do is we change our equations, and that means we change the lines or the planes which we can see, but what is not changing is the total intersection. The solution set is always fixed under these elementary transformations, and that's what makes it possible to solve the system using this method. So that is it for geometry of linear systems.